Good morning, students. Today we are going to start a new topic, that is band theory of solids, in which you are going to understand the different properties of material, that is insulating property, semiconductor property, as well as metallic property. In this particular unit, you are going to see especially the two things. First one is the behavior of electron in a periodic potential of a crystal. The second one is you are going to see the classification of materials such as metals, semiconductors and insulators. The main objective of this particular band theory of solids is to understand the basic classification of materials. What is the origin behind this basic classification? How do you classify the materials into metals, semiconductors and insulators? What is the origin behind it? That's what you are going to understand in band theory of solids. So the basic concepts that we are going to deal in this particular topic is, first we'll start with free electron theory of metals. It's also known as classical free electron theory of metals or Drude-Lorentz theory. Second one, Bloch theorem. And third one, which is very important to understand the classification of materials, that is Ronick-Penny model. This also explains why there are energy band gaps in materials. That means Ronick-Penny model explains the origin behind energy band gaps in solids, followed by the continuous concepts such as EK diagram, origin of energy bands, types of electronic materials, and finally we'll be seeing the effective mass of electron. So these are the basic idea of what we are going to see in next coming, let us say, 6 to 7 classes. So today we are going to start with the classical free electron theory of metals. It's also known as Drude-Lorentz theory. In this particular classical free electron theory of metals, we will be understanding what are the postulates or the assumptions made by Drude and Lorentz in order to explain the properties of metals. Followed by, we will be verifying the Ohm's law in metals using this particular free electron theory of metals. Followed by the merits of Drude-Lorentz theory as well as demerits of Drude-Lorentz theory. This is what we are going to see in today's class. Now, coming to the postulates of classical free electron theory of metals or Drude-Lorentz theory. Drude and Lorentz given some postulates in 1900 about the properties of metals. Especially these postulates made by Drude and Lorentz tries to explain some of the properties of metals. The first postulate is electrons moves around the nucleus in the atoms and such atoms are present in the metal. This is the first postulate. The first postulate is there are electrons which are revolving around the nucleus of atoms and such atoms are present in the metal. The second postulate is there are electrons which are free to move in entire space of the metal. These are known as valence electrons, and these valence electrons forms something known as electron gas. It means these valence electrons are allowed to move in entire space of the or entire volume of the metal. These electrons which are freely moving in the volume of the metal are forming something called electron gas. And coming to the third postulate made by Drude and Lorentz is that these free electrons which are moving in the metal, they experience a uniform potential. That means the electrons are moving in a uniform potential. This is one of the important assumptions that made by Drude and Lorentz in their theory. Followed by, they also assumed that these free electrons obey the classical free electron theory, the classical theory of gases, or the classical kinetic theory of gases. Just like our gases which obey the kinetic theory, the electrons which are moving in the metal also obey this kinetic theory of gases. Finally, they also assumed that the velocities of these free electrons which are moving in the metal obeys classical Maxwell-Boltzmann law. That means if you see the classical Boltzmann law of velocities, it is proportional to v square into exponential to the power of minus v square. That means it tells about the most probable velocities that can be obtained by these electrons. So these are the various assumptions or the postulates made by Drude and Lorentz in order to explain the properties of metals. In continuation of these postulates, they also understood the 2 points that, for example, if there is no electric field is applied across your metal, that means in the absence of electric field, these electrons move in random directions and they collide with other electrons or atoms or impurities, and hence their resultant movement is zero. In other words, in absence of electric field, the resultant movement of electrons is zero due to their random motion, and hence they cannot constitute any electric current in the absence of electric field. We know that if you wanted to have electric current, there will be a steady flow of electrons in a particular direction. In absence of electric field, that is not possible. On the other hand, you can see in presence of electric field, these freely moving electrons will be accelerated in a particular direction which is governed by the applied electric field, and hence they get net movement which constitute a net current in the metal. That means metals conduct electricity in presence of electric field, whereas they don't conduct electricity in absence of electric field. You can see the schematic of in presence of electric field and in absence of electric field, how the electrons behave inside the metal. You can see in the first figure, if E is equal to 0, because of random motion of electrons, they don't get net movement and hence the net current is 0. On the other hand, if E is not equal to 0, that means in presence of electric field, they get a net movement in a particular direction so that they constitute a non-zero current in the metal. So these are the basic ideas or the postulates given by Drude and Lorentz in order to understand some of the properties. After giving the postulates of Drude-Lorentz theory, it is important to understand the verification of Ohm's law in metals from the assumptions made by Drude and Lorentz. That means we are going to understand here the electrical conductivity of metals from Drude-Lorentz theory. This is also known as verification of Ohm's law. We start our discussion with in absence of electric field, what is the situation in metals? If you see the electrons which are moving in random direction, and hence there is no net velocity, and hence they don't produce any current in absence of electric field. On the other hand, in presence of electric field, you can see in presence of electric field means E is not equal to 0. You can see here there is a acceleration of electrons in a particular direction which is given by this electric field. For example, this is the negative and positive terminal of the battery. You can see the electrons are moving towards the positive terminal, so that they are producing a net movement in a particular direction, so that they constitute some non-zero current in presence of electric field. Here, the net velocity obtained by the electrons in presence of electric field is also known as something called drift velocity, which is represented by V suffix d. Drift velocity means what? The net average velocity obtained by electrons in presence of electric field is known as drift velocity, which is the responsible for the net current in presence of electric field in case of metals. To understand it further, look at here. I have considered a metal of length L and whose cross section is capital A. To this particular metal, I have applied some electric field. Now let us see what happens if you apply the electric field to this particular metal. We know that whenever there is an electric field, the electrons experience a force which is known as electrostatic force. That means the free electrons which are present in the metal experience an electrostatic force which is given by small e into capital E in presence of electric field. Small e represents the charge of electron. I am considering here only the magnitude. On the other hand, if you take capital E, this represents the applied electric field. F suffix E represents the electrostatic force experienced by the free electrons in presence of electric field E, capital E. Now, we also know that this is the force 1 which is experienced by the electrons in presence of electric field. On the other hand, these electrons are also experiencing some other force which is known as collision force or reaction force or damping force. Let us try to understand what do you mean by this collision force or reaction force or damping force. We know that electrons are in motion. When they are moving, they are having some collisions with their neighbor, such as electrons or impurities or some other atoms, right? So, because of this collision, they are actually experiencing a force which is known as collision force. Because of collisions with other atoms or impurities or other electrons, these electrons are actually experiencing some force which is known as collision force. This collision force is generally given by m into V suffix d over tau. Here m represents the mass of the electron, V suffix d represents the drift velocity, and tau represents relaxation time or collision time. Here the relaxation time or collision time represents that it is the time in which the electron has traveled between two successive collisions. That means between two successive collisions, electron is traveling for some time. That particular time we are calling it as relaxation time or collision time. So the collision force or reaction force is given by mvd by tau. Now electron is experiencing two forces. One is damping force or collision force, and the second one is electrostatic force in presence of electric field. You can see, if you want to have a net movement of electrons in a particular direction, the applied electric field force must be minimum of this reaction force. What do you mean by that? That means if you wanted to have a net movement of electrons, we need to overcome the collision force. That means the minimum force that we have to apply on these electrons by electrostatic force, that is nothing but F reaction. That means minimum force F reaction has to be supplied by our electrostatic force. That means if you want to have a steady state flow of electrons, the minimum electrostatic force must be equal to the collision force. If you are producing or if you are giving a force which is minimum of collision force, then only you can expect a net resultant acceleration in a particular direction driven by your electric field. That's the reason why for steady state flow of electrons, the minimum electrostatic force must be equal to the collision force. Under this condition, you just substitute Fe is equal to F reaction, where Fe is equal to E into E and F reaction is equal to mVd by tau. From this expression, I have just written the expression for drift velocity. That is nothing but small e into capital E into tau by m. This is nothing but E tau by m. This is the basic expression for the drift velocity obtained by these electrons in presence of electric field. Now let us try to understand how this drift velocity is related to our Ohm's law. In other words, is how is going to be included in our Ohm's law. To understand the verification of Ohm's law in metals from the Drude-Lorentz theory, let us start our discussion from the basic definition that is known as the current density. Current density is nothing but what? The net current which is flowing through a unit cross-sectional area. That means what? The current I divided by cross-sectional area A. That is nothing but J. Current density J is equal to I by A. And we know that the current is defined as charge per unit time. That means Q by T. And we also know that the total charge present in a given area is nothing but N into E. N represents the total number of electrons, E represents charge of the electron. Q is equal to N into E, it represents the total charge. So substitute Q is equal to NE. We will get N into E by T into A. Fine. Now in this expression I am just multiplying and dividing with capital L, which is nothing but the length of our metal. Here if you substitute L in the denominator and the numerator, you can see there is A into L, area into length, which represents the volume of the metal. Just substitute A into L is equal to volume. Now what you will get here? N into E into L divided by T into V. V means here the volume of the metal. But we also know that here the number of electrons per unit volume is nothing but the number density of electrons, which is represented by small n. Now substitute capital N by V is equal to small n. Then you will get the current density J is equal to small n E capital L divided by T. And here you can see again L by T. L means length by T means time. So this represents velocity. We are talking about the behavior of electron in presence of electric field. So velocity I am representing with the drift velocity. Now L by T represents here the drift velocity. Then what will happen to your current density? Current density J is equal to small n small e into V suffix D. This is the basic expression for the current density in terms of your drift velocity. Now we also know that the expression for drift velocity from equation number 3. What is that? Vt is equal to E tau by m. Then substitute Vt is equal to E tau by m in equation number 4. What you will get? J is equal to Ne square tau by m into E. For a given metal, if you see the value which is there in brackets, that is Ne square by tau by m, is constant. For a given temperature, for a given metal, this value is constant. I am representing this constant with sigma. This sigma is generally known as conductivity of the metal. So J is equal to sigma into E, which implies that conductivity is equal to Ne square tau by m, which is a constant for a given metal at a given temperature. So if you rewrite this equation number 5, what you can understand is the current density J is proportional to the applied electric field, which is nothing but what? The Ohm's law. We already know, according to Ohm's law, the current is proportional to applied voltage. Here I am just taking current density is proportional to the electric field. Electric field is nothing but what? The voltage applied per unit length. That is nothing but electric field. Current density means the current per unit area. So both are proportional quantities. So we can say that this is another form of Ohm's law. Another form of Ohm's law, according to which the current density is proportional to the applied electric field. That's how we have verified the Ohm's law by using the basic assumptions of Drude-Lorentz theory. We have seen basic assumptions. What we have taken? In presence of electric field, the electrons get net movement and they constitute current, and they also experience a force of electrostatic force, which must be equal to the reaction force in order to get the net movement. So from these assumptions we have verified that metals obey the Ohm's law. So this has been verified. Here we can also convert the conductivity in terms of something called resistivity, which are actually related as rho is equal to 1 over sigma. Both are inversely proportional to each other, which is nothing but, that means the resistivity of the metal is given by m over Ne square tau. So you may expect problems based on this particular expression, that is rho or sigma. They may ask anything. Either they may ask you to calculate the resistivity or conductivity, so for which we know the expression from this particular note. So this is nothing but the verification of Ohm's law from Drude-Lorentz theory. Now let us try to understand what are the merits of Drude-Lorentz theory. By taking the postulates of this Drude-Lorentz theory, they were able to explain the Ohm's law in metals, or they were able to verify the Ohm's law in metals, which is the asset. Second one, they were able to explain the electrical and thermal conductivity of metals, along with the optical properties of metals. They were able to explain electrical and thermal conductivity as well as the optical property of metals, including the verification of Ohm's law in metals. These are the particular merits of this Drude-Lorentz theory. On the other hand, what are the demerits or drawbacks of this particular Drude-Lorentz theory? The drawbacks includes the Drude-Lorentz theory could not explain the concept of photoelectric effect and black body radiation in metals. They were not able to explain the photoelectric effect and black body radiation from their theory. Second one, they were also failed to explain the electrical conductivity of insulators and semiconductors. They were able to explain successfully about the electrical conductivity of metals, but they were not able to explain the electrical conductivity of insulators and semiconductors. Finally, the theory failed to explain the magnetic properties and specific heat of metals. These are nothing but some of the drawbacks of Drude-Lorentz theory. Thank you.